So far we have seen that the Gibbs free energy change for a reaction tells us something about spontaneity, right? If we remember that our Gibbs free energy change is negative, that reaction or process is spontaneous. Well, it's built up of two pieces, right? The enthalpy change for a reaction and the entropy change for a reaction. And we'll see that the signs of each of those contribute either positively or negatively to a spontaneous process. So if we want to have a negative delta G, right, that would be a spontaneous process. Well, that could happen if we have a negative delta H, right, and a positive delta S. That means that, and no matter the temperature, right, our reaction is spontaneous because this is always a positive value. It's in Kelvin, right? So here, if we have a negative delta H, negative delta S, okay, we'll notice that this is spontaneous for all temperatures. Well, if we have the opposite, positive delta H, negative delta S, that will mean our delta G will always be positive, and we'll see this instance is non-spontaneous for all temperatures. Okay. Now, what if we have conflicting contributions? Like, let's say both our delta H and our delta S are negative. Well, that means that our delta G value could be positive or negative, right? And so what we'll see here is that the spontaneity is temperature dependent. Okay. So we'll notice at low temperatures, our enthalpy is the main contribution to spontaneity, right? And then as our temperature increases, it's going to make this contribution greater and greater and greater. And at some point, it becomes non-spontaneous, okay? And so what we'll see at low temperatures is going to be spontaneous. We also have the possibility where we have both of these being positive. So again, we have the ability for delta G to be negative or positive depending on the temperature, depending on how this value changes based upon temperature. So again, our spontaneity is temperature dependent, but now the opposite is true. If we have a low temperature, this value is going to be smaller in magnitude than this value, and so that means that it's overall going to be non-spontaneous at a low temperature. Eventually, if we increase the temperature, increase the temperature, increase the temperature, this value becomes a bigger contribution to our spontaneity, and at some point becomes greater than our enthalpy, and it becomes negative. And so we'll see here that would be at a high temperature. Now let's go ahead and look at an example of what this looks like. Okay, so let's say we're going to deal with mercury undergoing evaporation. Okay, so mercury liquid to mercury as a gas. Okay, now we think about this. If you have water evaporate, we think, is the enthalpy negative or positive? Well, that enthalpy, what we're going to see, is positive. We have to add energy in to make something evaporate. So if we actually looked at the enthalpy change of this process, we would see that it is positive 60.7 kilojoules. Right, which makes sense. We've got to add heat in to make that reaction happen. We also look at the entropy change of this. Well, for a liquid to a gas transition, we are going from a liquid state to a gaseous state. The gaseous state has a greater entropy than the liquid state. So we'll see that our entropy should be positive, right, the change. And so we'll see that it's actually 98.9 joules per mole Kelvin. And we could say this is kilojoules per mole. Okay. So now we see these are in conflict with each other, right? Positive delta H, positive delta S. At a low temperature, it's non-spontaneous for this to happen by itself, right? It's like at 80 degrees Celsius, your water doesn't just boil. At 100 degrees Celsius, your water starts boiling, right? It becomes spontaneous for that to happen. Similar thing here that we can see for our mercury. We want to actually figure out, well, at what temperature does this become spontaneous? Okay. Well, if we start non-spontaneous, that's a positive delta G. When it's spontaneous, that's a negative delta G. Well, what number does it got to go through to make that happen? 0. Right? As you go from positive to negative, you got to cross 0. So what we'll see is that when our delta G equals 0, we go through the transition from spontaneous to non-spontaneous, or non-spontaneous to spontaneous, depending on the temperature dependence. And so we want to figure out what point does delta G equal 0? Well, we have our two values of our enthalpy and our entropy. So we see that this is 60.7 kilojoules minus our temperature that we don't know, right? That's what we want to solve for. And then we can go ahead and see, well, then we multiply by our entropy. Well, let's go ahead and make sure we keep our units talking to each other, right? Kilojoules, this is in joules. We probably want to convert that to kilojoules. So we would get 0.0989 kilojoules, okay? And so now we see we have an algebraic expression where we only have one unknown. We can go ahead and solve for that, right? We can bring this value over here. So we get 0.0989 times our temperature, and just kind of as a reminder, this isn't going to be in Kelvin, equals 60.7 kilojoules. We can go ahead and finish off solving this, and we would find that the temperature in Kelvin that our transition occurs is 614 Kelvin. Okay, so we think, what does that mean for us with regards to mercury? Below that temperature, it's non-spontaneous for mercury to go from liquid to gas. Above that temperature, it's spontaneous for mercury to go from liquid to gas. Well, what would we call that place? Well, we would call that temperature. That would be our boiling point. It's like the one that we're used to, water. Well, water at 80 degrees Celsius is non-spontaneous, below our boiling point. Water that we get up to 120 degrees Celsius is spontaneous for it to go from a liquid to a gas, right? Well, what is the place that happens? Our boiling point, 100 degrees Celsius. So we see if we look at these phase transitions, we have the ability to calculate boiling point or melting point if we did like solid to liquid, if we knew the enthalpy and entropy changes for those, right? And we say that they go through the place where our Gibbs free energy change is 0, as we go from spontaneous to non-spontaneous and vice versa. So hopefully this gives us a good idea how we can use our enthalpy change and entropy changes specifically for maybe a phase change or a reaction, that we can predict where a reaction becomes spontaneous or non-spontaneous if it's temperature dependent like these two examples.